Chris told me my requirement was too strong. It should be a little bit. So I said it has to be a complement in C. So now it actually one has to require Cx, and this is basically the following. If you have a point, let me just explain what Cx is here. If you just look at our Rk, then if you have a point, and this is you have a point with coordinate A here and then plus in W, then if this is 0 here, you would define it to be the whole quadrant. Now, if you are here, then you just take this half space plus omega. That would be Cx. So it would be a little bit larger space. So the Cx is a cone of direction you can walk into by staying in C. So if x is an interior point, you can walk in any direction, then Cx would actually be the whole space E. If you're on the boundary, Cx is just in the direction you can walk. If you are at this corner here, you can only walk in the direction of C. If you are here, you can walk in the direction of the half space. So my condition, which I wrote, was you can find such retractions, but it's too restrictive. The right thing is to find a complement in this one. It's usually bigger than C. Okay. So now, if we are dealing with, so let's be tame, then let me define the following. So CDX, this is TXO intersected with the half spaces you lie in. So let me explain this in this example. So this segment, this quadrant is the intersection of half spaces. Say H, another, which will be on this side, another half space on this side. So you have, if you have Rk, there are k different half spaces. And if x lies in the interior, so then this would be all of C. And is this right? So what is I? Let me just see. I have to get this right here. What is, Chris, remind me. Yes, I just let me try to figure out what I mean here, actually. So what do I mean here? I mean, I'm sure I know what I mean, but I don't know what I wrote here. So, okay. Oh, no, it's not the. Okay. So, okay. So, so let me. Okay. So let me in this for this particular situation, which you may assume, and C is 0 infinity k plus W. So then we have the spaces EI, which consists of all AW, that AI is equal to 0. So this would be the hyperplanes, these guys. So then we have the half spaces HI, which are all A, W, such that AI is greater or equal to 0. And then I define, so where is this now? I of x, and I of x are the set of indices where I'm in EI. Okay. So then I of x is all indices that x lies in EI. So I look at all indices that lie in this hyperspace. So for example, if I'm in the interior, I of x is empty. So then this here would be what? What is the empty intersection over the empty cells presumably everything, yeah? TXO. And if I'm an honest boundary point, then I would be precisely in one EI. Then I would take this half space associated with intersected with the tangent space. So that would be a particular quadrant. The worst situation is I'm in this corner here, then this would actually be C. C intersected with Tx of O. So this is basically in the tangent space the directions you can go without falling out of your manifold or of your polyfold. The linearized version of this. CXO. So that is basically the cone in the tangent space of O. Yeah, D is because of this D index. It has something to do with the degeneracy. So that is basically, if you look at the tangent space and you're on the boundary, which direction you can go without falling out of your manifold. So these are all partial quadrants which vary on the point X. So that is just part of the notation. If you don't like it, I'll tell you. Yes. I mean, you can define this, but it wouldn't have any specific meaning. But it no, yes, you can define this. But let me put D here. Let me put D. This is part of the notation because otherwise I'm okay. So let me put this, and then let me define. Okay, so I answer your question in a second. TXO is TXO intersected with all I in EX EI. So this is the intersection of all these hyperplanes here. So for example, if you had this point, it would be just a W. So you have the following inclusions. You have TD of X, which is a linear space, is contained in CDX of O, which is a partial quadrant, and that is part of your tangent space. Yeah, it's part of the notation. Otherwise, this is different from this one. So otherwise, I wouldn't put D's here. So I don't. Of course, I could put not a D. Oh, okay, so I'll think about it. Yeah? So what it is so this here is a partial quadrant in this thing. It depends on X. And this is, in some sense, the maximal linear subspace living in that partial quadrant. So now, so you could define this for tame or not tame. But now comes result is theorem. If OCE are tame, and F from O into O prime is an SC diffeomorphism, then the following holds. DO F of X is D O prime is DO F of X. So that is this measure of degeneracy for all X. And of X, yes. Then if X is smooth, O infinity, so for what I'm writing down, it has to be on the level 1 or higher. Then TF of X of CDX O is CD f of x O prime. So these things are being preserved. And Tf of x, TD x O is yeah, so it only has to be a germ, so you may assume of A being small around the point. So this is a local property. If you have an SC diffeomorphism, this structures, which is tame, it preserves these structures. That are, in fact, are the reasons why it sort of sees the boundary and how complicated the boundary is. That's so tame. Why is what?
Why do these results reflect tame?
Yeah, because otherwise it's wrong. Yeah, the thing is, you know, okay, so this is of course tautological, which is, but it's the same than dc of f of x. So this is what you can say. Okay, so this is what you can say if this is dc prime. So you have a particular so this is tautological here, because that is a diffeomorphism invariant. But it's a statement about how you lie with respect to the boundary for you to retract. So the non-trivial statement is this here. Because, you know, these things here are obtained by intersections of the tangent space with things of the ambient space. If you are not in a particular good position with respect to the ambient space, these things are not being preserved. I mean, that's a non-trivial statement here. And this only can happen because the tangent space of O lies in a non-trivial position to the boundary of C. Yeah, so I think what would be here, so it would be here so let's see if this is a retract. So for example, this DC number would be 2 here as a retract at this point. And here it would only be 1. But obviously, this thing is diffeomorphic to this one. So then what is a cone? So I don't know if that works in this low dimension example here. So this in fact, here you would have yeah, maybe the example is too low dimension. So in this example, at least this would not be equal here.
Why is the number 2?
Yeah, because the degeneracy index of this, in this case, can be defined by the degeneracy of the point with respect to that ambient space. And here it's a corner point, it's 2.
I thought you were defining it as
Yeah, the thing is, of course, this is a bad position, so if you want to construct that space as a retract, you would rather construct it like this.
I thought you were defining it as the infimum overall.
Yes, then it's 1. Yes, right. You're correct. So if you would have this as a retract and define, then obviously this is a polyfold, then you would define the D of this by taking different charts like this one, and it would be 0. But nevertheless, now when I define these guys here, these guys are defined with respect to the ambient space. And if then you don't have a priori a good position, then there's no reason why this should be preserved. These things here are defined by intersections with things in the ambient space.
I thought you defined it as
No. The number is defined as the infimum, but this cones here. I mean, this is trivial here.
Oh, the cones.
Yeah, but this, well, all these cones, they're defined with respect to the ambient space.
Oh, I see.
And then if you don't lie in a good position to this, I mean, you have to lie, in general, in the best position to the space to define it. And I'm just saying, if it's tame, it lies in the best possible position already.
Sorry, can we
Yeah.
go back to the issue of SC complements? I kind of got confused with all the notation changes that you erased.
There were no. You want to cause trouble, huh? So what means notation changes with SC?
So you had written before that TXO and E has an SC complement of W and C, but then you said that
Yeah, it should be CX. Yeah,
CX, but then you decorated CX with a D.
that's a different. That's already something else.
Okay.
Maybe it's the same, but anyway. So yeah, yes. Okay. Yeah, this. It's a. The CX is actually the T. Yes, right. Yes, it's actually this. Okay, okay. So you can also call it CX at this point. So Chris will think about it if we need a D there or not. Yeah, this is a point here. The other was also a point. This is not the manifold. This is a point X.
So these things are not diffeomorphisms, right?
No, they are.
They are.
Yes, but because these are tame retractions. They are defined extrinsically, but if you have diffeomorphisms with two retractions, they are being preserved.
You just write the definition of the SC complement. No, this is the definition. Yeah, but he said that the SC complement was like W and C.
Yeah, so. So this has a complement. So as a subset in E has an SC complement in CX, which was defined.
I thought you said these two examples are diffeomorphic.
Right, but what I'm saying is, if you want to define this intrinsic if you want to define what actually is intrinsic structure like this, but which however is extrinsically defined, then you better put that retract in a good position to C. And tameness is precisely such a condition. I mean, maybe I can define it intrinsically, I don't know. But the thing is,
Oh, I see. I think I see what you're saying. So there's a subclass of things which are tame.
there's a subclass of things which are tame, and they lie in a rather good position to the boundary of C. And then I can put additional structure on those guys by using structures of C, like this half planes and so on. And then it turns out that these are actually diffeomorphism invariants. So that is. And if you would take this here, maybe it works because it's one dimension, I don't know. If you take this and define this extrinsic things on it, then that would not be necessarily diffeomorphism invariant. You can only define this if it's really the retract lies in general position to the boundary. So now then some other things which are important. So X be tame. So this is shorter to write than saying X is a polyfold with boundary and corners. Yeah. So X is tame. Then a phase is the closure of a connected component of the set of all x with dx of x equal to 1. So in this example here, so if I take all points with d of x equal to 1, I have to remove this point. So this is a component here, and this is a component. So if I then take the closure, that would be a face, and that would be a face. So now you have to keep that example also in mind. Everything is round. You have a corner here. Then locally you have two faces, but globally only one. So now, say x is phase structured. Another definition. If every point lies in precisely dx of x many faces. So this is not phase structured because this point here has d of x equals to 2, but it lies in precisely one phase. So this is phase structured here. This thing would be phase structured. So locally, this is always true. Locally, so if you take a neighborhood, then each point there lies in precisely as many phases as its index tells you. So here's a theorem. So let x be tame and phase structured. Then a phase is a phase structured sub-M polyfold, and if I take the inclusion of a phase into X, obviously we have d x of I of x is d f of x plus 1. Now, so the phases are really nice things in this case. Also, what is true, the intersection of finitely many phases is also an M polyfold. A tame one. So now you see, this is actually quite important for symplectic field theory, that you have a nice structure of the boundaries. Where the boundaries, or if you do Floer theory and you look at gradient lines, but do it by Fredholm theory, you look at the connecting spaces, the broken trajectories. That is also phase structured, and the index measures precisely how many breaks. These are broken lines. How often it's broken. If it's broken once, it's a boundary point. Broken twice, it's a d equals 2 point. And then the boundary strata are the things which are precisely, the phases are the closures of the things which are precisely broken once, of the connected components of things broken once. And there are also M polyfolds with boundary, in this case, M polyfolds with boundary and corners and so on. So the geometry is really nice there. So as good as it can be. So now we come to something where I know something to say, but I also have a question. So what should be the definition of a finite dimensional submanifold? So how would you define this? So you have tame. I want to define a finite dimensional submanifold. I already defined subpolyfolds. Yes, so it should have, at least if I'm not at the boundary, it should have the structure. The induced structure, polyfold structure, is actually equivalent to induced is the same as a manifold structure. So that means there's an atlas, which a manifold atlas, which is compatible as a polyfold structure with the other one. So here is so A is called a smooth finite dimensional submanifold. Provided A is an SC smooth retract and the following holds. A equals A infinity. So this means the first thing, all points are smooth, yeah, or on the infinity level. And this second thing, so since now every point is smooth, every point has a tangent space. Yeah? If you have non-smooth points on the level 0, they don't have a tangent space. So for every A in A, the dimension of TAA is finite and locally constant. So up to this point, it looks like that should be the definition. Yeah? So you have a subpolyfold that has a tangent space. The tangent space has the same dimension, but it might not be true. So I have to add something to it, and then I will ask a question. So for every point A in A, there exists a retraction so that R from U into U1. So observe, since everything consists out of smooth points, the image of any point, R of x of any point, is a smooth point. So it in particular goes into where the index is lifted by 1. So that R is SC infinity. So if I take the U but lift the index by 1, it should still be S infinity. So then that looks like a good definition, and this definition of a submanifold is at least consistent with our Fredholm theory. Our Fredholm theory produces this solution spaces here. So when we do the Fredholm theory, we get solution spaces when things are generic, which are subspaces of this kind. In particular, they have, as it turns out, they have a natural smooth structure as a manifold. So what happens is, in local coordinates, so if you go to local coordinates, it's 1. The index is lifted by 1. U is U of A. So this thing retracts onto A, but you retract with a better differentiability than you usually have. If usually I say R from U into U is SC smooth. Now I require into U1 is SC smooth. So it means the map from U0 to U1 is SC smooth, which means the map from level 1 to level 1 is C1 in particular. Now, so I don't say anything about how this thing lies with respect to the boundary. So near the boundary, it might look very bad. It could be, for example, this pyramid could satisfy this. So if you have property 1, 2, and 3, and you go to local coordinates, you take a point A, you have this tangent space, you take a complement of this. So you can take so this here is the kernel of the identity minus dr of A. You take the kernel of dr of A, for example. Then you can write, then it turns out that A, which lies here, suppose A is, this is 0. You go through the point 0. Then you can write locally A as a graph of a map from here to here. So you can write it as A goes to A comma B of A where b of 0 is 0 and db of 0 is 0, and this is a smooth map, classically smooth, into any level. So the A locally then, if this is a tangent space, looks like this as a graph. So, and when one proves this, one needs this property. So my question is it true that this holds? So and this graph here, I get the entire, everything which lies in the neighborhood of this point lies on this graph. So every point in A, in the neighborhood, lies on this graph. So now this definition looks a little bit odd. Why do I need more differentiability here? And I don't know. I mean, I could not prove that I could not exclude the following case. The thing is, you could have, so one shouldn't draw it in finite dimensions. It must have to do something with infinite dimensions. You could have this picture here. You could have perhaps that things, so what you can show is, without this condition here, you can show that you capture a certain part. So if you pick any point in the retraction, you can find a smooth submanifold which lies in A, given as a graph. But you could never show the things are isolated. So it could be that there are other things coming to it, and if I take the tangent space here and write it as a graph, I recapture this thing here. But there's something going away quite flatly, and the thing is, you can always try to go away because you have in a really sneaky way, because you have this infinite dimension directions. So it is quite possible that in general, if you don't have this condition here, the retracts which satisfy this are actually branched manifolds. Could be possible. I mean, it has to find some examples. So the things could look like things go off, but always it's possible that you have retracts of this kind, smooth retracts, if you don't require that stronger smoothness here. That I don't know. But the problem was I could always recover this thing here, but I could show. But when I did the estimate, I could never show that this is an isolated phenomenon. So there could always be, from certain directions, this infinite dimensional space, things come, but they would actually have the same tangent space here. So therefore, I have a well-defined tangent space of constant dimension. So that's possible. Of course, in finite, if I embed it into a finite dimensional space, this thing here in the neighborhood doesn't seem to be a retract. But it's possible if you embed this, if you embed something like this, where this goes off here, if you embed this into an infinite dimensional space, that this might be a smooth retract. So it would be nice to understand. So for our Fredholm theory, we get things like this. But nevertheless, it raises the question, this looks like a natural definition of a manifold here, I would say, but it might not be. Yeah?
Question about the third condition. So U is unable to be of A inside X.
Yeah.
And R is a retraction such that the image of R
Is
A intersected Q.
yes.
But A is A infinity. So in particular, A is equal to A superscript 1.
Yes, but it doesn't mean that you actually smooth into that space because they take different norms. This is still infinite dimensional. I mean, the thing is, the image is not in a fixed subspace. The image varies around. The image is sort of, if you linearize, finite dimensional. But it might make very wild turns. And then it becomes a measurement issue how differentiable it is. Yes, but the images, even if the linearization, they can make fantastic turns. So different norms play a role. And And the issue is actually if things are isolated or not. Like I always can discover this by this thing, but there might be something coming from certain directions where, in fact, the difference of the norms on different level blows up. Like, so you control the 0 norm, but the 1 norm seems to go to infinity. And so on. So there's some interesting stuff happening. So now so there's a little bit more one could say, which I'm, however, not going to say or write down. Is so maybe I should. Yeah, maybe it's good to know. So, okay. Assume this is a smooth submanifold. Yeah? So conditions 1 to 3. Now, near the bound, so I didn't require, so it just means it's a retract which has a sufficient amount of differentiability properties. When I retract it, it has a constant tangent space and so on. So when can I say that that is actually a manifold with boundary and corners? So in general, not, because the example, you could fit this example of the pyramid into this, because I don't require how that sits with respect to the boundary. So for example, one should be able to define A as in general position to the boundary. If A is in general position to the boundary, it should be a submanifold with boundary and corners. But there are things which are not in good position to the boundary, but still inherit a structure as a manifold with boundary and corners. So here's a good criterion for this. If I can find this. So, which page are my notes? What?
Well, you're going to write the example from your notes, so tell us what page it's on.
Well, how does it matter? Because you don't get the notes, or you get them? Page 30. Okay, so let me first make a definition. Yes. Did Katrin pay you or what? Okay, so let N be a finite dimensional subspace. So I want to define first what it means to be in good position to the boundary. So I have a partial quadrant. I have this here. So let N be a finite dimensional subspace, and then we say N is in good position to the boundary, provided the following holds. So first, N has a SC complement. And then the following holds. It has a SC complement, and there exists an epsilon positive, so that for all say NP in N plus P with the norm of P is less or equal, say on the 0 level, is less or equal to the norm of N on the 0 level. The following statements are equivalent. Okay, so N is a finite dimensional subspace. Actually, it should consist out of smooth, so this is a space with SC structure. So let me write smooth here. Smooth means it's all points in N are on the infinity level. Otherwise, it cannot have a complement. Then we say n is in good position to the boundary, provided n has an SC complement here, there exists an epsilon, so that for all points, so this is in some sense a thickening around n. Yeah? It's like a conical structure around n. Points of this kind. The following is equivalent. N is in C is equivalent to n plus p is in C. So here's the example. I mean, if the subspace is that side here, it's not in good position. But if it looks like this, then you can have some kind of this conical thing there. And if it takes a complement like this, then this plus a vector here lies in the cone provided precisely when this lies in there. Yeah, if this is small enough, you'll see even here, if you lie in this cone, so that's some kind of a stability condition. And it's clear, it's even very important for Friedholm theory. If the kernel lies in a good position like this, then of course if this is the kernel of the operator and the operator is surjective, then the solution space would sort of here would be tangent at this point and would move out. So it would live for a small while in this. Also, what is true is if you take n here, the subspace, and intersect it with C, then this intersection is actually a quadrant. So this example with the pyramid is an example where the pyramid was obtained by taking a three-dimensional manifold, a three-dimensional subspace in a four-dimensional quadrant. But it was not in good position, because if it would be in good position, the degeneracy on the top would be 3. So good position means some kind of stability in this criterion if I'm in C or not. Yeah? You can deviate a little bit as long as the deviation can be measured with respect to this component, these are equivalent statements. So now, here is then the result. So we start. So I want to say that A actually is a nice manifold near the boundary. So we have theorem X tame in X smooth finite dimensional manifold, so that for every A in A, T A which of course lies in TA of X, is in good position to, well, here was a D, CDX X. So since these things were preserved, there's a well-defined meaning for this cones in X. Yeah? I showed you if you have tame maps, then the cone for this retract is mapped to the other cones. So it means there's an intrinsic notion for tame manifolds for these cones. So this here is, for example, so this is A here. So if A is an interior point, this is everything, so there's no condition. Yeah? If A is a boundary point, then this is a half space here. And in good position like this means if you have a half space, obviously lying like this is not a good position. You should rather lie like this. That's what it means. So you have this cone, and then you know if the point n plus p lies in the cone, is equivalent that the projection to this is in the cone. Then if you have a more complicated thing like this, it would say that it looks like this. So now, under these conditions, then A is tame. So it means the following. So first of all, this has a structure of a manifold, but tame means actually it can be this structure induced on this A can be obtained by tame retract. So it's actually a manifold with boundary and corners. So that hits the boundary nicely, that it has that the induced structure is actually that of a manifold with boundary and corners. So that's the test. So if you have something which might be like this pyramid, and you make the test and that corner, you would find out that the stuff doesn't lie in good position. But if you find it's a good position, then this higher singularities don't occur. So you can test this. So then in SFT and so on, we in general cannot show that the solution spaces are in general positions to the boundary, but we can show, and there are of course certain iteratively procedures that we can always generically make them in good position to the boundary.
Yeah, I don't think you said what good position.
No, I said what good position was. Is here. You need an SC Banach space and a finite dimensional subspace. And here, this is your finite dimensional subspace. This is your SC Banach space, and that is this quadrant in the subspace. So this is your E, this is your C, and this is your N. Good position. I said good.
Are they isomorphic?
No. Good position and general position is not isomorphic. Here, a one-dimensional subspace. But in general position to this, you have to be two-dimensional.
Yeah,
At this point.
I understand what general position is. I understand the good position.
Good position is this. So good position. So here, this is, for example, in good position. Because the thing is, there is a complement, and there's some kind of a conical structure. And if you take a vector here, which can be written as a vector n plus a vector p, then n plus p is in the cone if and only if n is in the cone. If you have this here, and I take this as a subspace, there's no conical structure with the property if n plus p is in the cone, the other is in the cone. Yeah. So that is good position. And it looks sort of trivial in low dimensions, 1, 2, 3, but in 4 dimensions it already means something. And so this is, so you can talk about good position if you have a partial quadrant and you have a Banach space in a finite dimensional subspace. You can say n is in good position to the partial quadrant. So now in this case here, the roles are being played. This is my finite dimensional subspace n. This is my Banach space E, and this here is my partial quadrant. And these are all intrinsic things defined for tame polyfold. And I can look how does a tangent space look with respect to that data associated with the M polyfold. And if it's in good position, I can conclude that the singularities I will see, for example, are always less or equal the dimension of the thing. This is D. And the pyramid was bad because the dimension is 3, that it shouldn't have a 4-dimensional singularity. So type 4 singularity, which is on the top. And if you look at so in Perturbation Theory 2, we have we studied this. There's in the appendix there are this consideration about good things and so on. And there we give an example of a 3-dimensional thing in the 4-dimensional, I think 3 and 4 or something like this, which is not in good position, and it hits it, and you have sort of this d equals 4 thing. So now, so we have, okay, so I will start with Perturbation Theory next week. So let me just finish finish something here. We haven't talked about bundles yet. And bundles one should talk about. because it's the bundles will be important and the structure of the bundles because of a perturbation theory. I want to have a Sachs-Smale type perturbation theory. So now, when we do applications, the applications will be concerned with differential operators of order at least 1. Yeah? So, if I study in differential, so whatever the order of the differential operator is, I will make the following normalization. My spaces have filtrations, the bundles will have filtrations, the movement should be horizontal. An M point in the base goes to an M point in the bundle. Okay, so now, if I study a manifold of maps containing H3 maps, and I apply a first order differential operator to it, I get H2 maps. But still it makes sense to talk about H3 objects, H3 sections along an, it's not me, obviously. It still makes, so it means if I have, say, an H3 map, the differential operator, say the D-bar operator, produces an H2 section along the H3U, yeah? So you have the underlying curve, you apply the Cauchy-Riemann operator, you get a section of a bundle with some kind of pullback bundle by U. But it's an H2 section of an H3 bundle. Yeah, so you pull back, say this omega 0, 1. Now U is an H3 thing. You pull back a particular smooth bundle by, you have a pullback bundle of a smooth bundle by a lousy map, an H3 map. So the transition maps of this bundle are H3. So the only type of sections you can talk about is, in the best possible case, about H3 type sections. However, the Cauchy-Riemann operator is very nice to you. It produces H2 sections which are well defined for H3 type bundles. But still, there's a good way to exploit this. Since we can talk about better quality of sections than we actually need, you can use this for a perturbation theory. In particular, since H3 goes compactly into H2. So what you want to do is, you want not to give this away and want to use it for the perturbation theory. So let me make that in abstract ways more precise. Consider now this wonderful thing, object here. So this is something like a product, but it's not entirely symmetric. So as a set is this, but it has a double filtration, MK, but where K lies like this. So a section of this trivial type of bundle here would have the property, if X is in UM, then S of X, which would be, of course here you get the X, would lie in UM plus FM. So in the case of the Cauchy-Riemann operator, I would start, say, with H3 here. I get an H3 here, and I get an H2 here. I would consider this as horizontal. But still, it would make sense to talk about okay. So now, if you have this thing here, then you can construct two SC spaces, depending if I is equals 0 or 1. This would be where the filtration is this. And you could construct this here, where the filtration is this. So now, what you want to look at are now bundle maps, and the bundle maps, they should be linear in the fibers. So you look at maps phi. They should preserve the double filtration, which we have. And phi should have the form xh is phi of x, a of x, h, and it should be linear in h. Yeah? So preserves double filtration. But observe that the filtration is constrained here. K can only run up to m plus 1. And what is the smoothness requirement? Since it preserves the double filtration, it would preserve in particular this filtration and this filtration here. So you require that. Is SC infinity for I equals 0 and 1. So these are the maps which you have. So they preserve this double filtration, which then can be, and there should be smooth in these two sense. If you first take the diagonal filtration here, that should be smooth, and the other one if you lift this by 1 here. So then you can now go with the whole series through. You can look at retractions in this category. Then you see this means in the base you have in particular retraction. And these are your local bundles. Then you can talk about tame retraction. Tame just means that the thing in the base is tame. And the things of interest are then the images of these guys. K, and you have an underlying retraction, produces a tame O, and of course you have a projection induced, and these are the local models for bundles. And they have a double filtration. And what is really important is that if you fix a fiber and you go from m plus 1 into kmm, that this in a fixed fiber is a compact inclusion if the scales are compact. And that is really important for the perturbation theory. So how long? 1 minute? So okay, so now we have this, we call a strong local bundle. And these are the local models for bundles. And then the transition maps are precisely the guys are prescribed. And a section of this bundle, a smooth section, is one which maps a point on level m to a point of character mm. And then, of course, there are interesting sections which make a point on level m to a point of the form m comma m plus 1. And these are in some sense quite compact sections, which are being used for the perturbation theory later on. Okay, so I think we stop at this point. Yes, so if you think about this here, it takes a while to digest it, because why do we have this double filtration and so on? So it allows a very quantitative perturbation theory. We can say what the sizes have to be. Yeah.
Do you ever actually make use of the double filtration? I know you make use of having two diagonal filtrations, sort of shift
Yeah, it's equivalent. If you control this, you control everything else. Yeah, you can look then if you take say m and here m minus 5, yeah, and the control this is all controlled by just these two guys. Well, in principle, yeah, you need maybe the m and the m plus 1. But you know. Yeah, right, but the thing is.
Define a scale Banach space with a double filtration. Yeah, you only provide scale structures where you have a filtration, not a double filtration.
No, but I mean, no. You definitely need. If you just have this diagonal filtration, the one, it doesn't work. Yes. Yeah, but then if you do this, then the others also preserve. I mean, it's just equivalent. So why do I just?
Why do you give us more than we need?
Because I love you. I don't know. So, yeah. Anyway, so we decided to have this double filtration, but it's right. All the smooth properties following by taking the mm or the m, m plus 1 filtration. And it's a taming device, in particular if you make bundle changes. So suppose you want to make a change of coordinates for a section. Then if x is on level m, this f of x is on level m, but the change you can do here also has to preserve level m plus 1. So that thing cannot be too wild. It constrains somewhat the change of coordinates you can do. And that's very important. Okay, I stop here now, and he can go.